These are the recorded lectures for slide set 2A, and we're starting with section 2.3, molecules and compounds. Both molecules and compounds are combinations of atoms, but there is a slight difference in their definition. A molecule is defined as two or more atoms bonded together, and it doesn't specify if the atoms are different or the same. So it can be two of the same atoms bonded together. A compound has to be at least two different atoms bonded together. So this is an example of a molecule and a compound, and it is the chemical formula for glucose, C6H12O6. It contains three different types of atoms: carbon, hydrogen, and oxygen. 6 atoms of carbon, 12 atoms of hydrogen, and 6 atoms of oxygen. And that makes one molecule of glucose, which is also known as blood sugar. So it is technically a compound, but we do tend to call it a molecule in biology, just because we do. Just because we do. So then we have a section on mixtures, where you have two or more components that are physically mixed. There are three basic types. Solutions are when you have one of the components dissolved in the other one. Then colloids and suspensions. In a solution, the particles are tiny, but they don't settle out and they don't scatter light. So mineral water is a solution. Salt water is a solution. Sugar dissolved in water is a solution. A colloid is when the solute particles are larger than they are in a solution, and they scatter light, but they don't settle out. So Jell-O is an example of a colloid. Blood is an example of a suspension. The solute particles are large. They settle out and they may scatter light. But you can spin blood in a centrifuge and the components will settle based on their density. So all the red blood cells will settle at the bottom, and then you have your plasma, and then the white blood cells and platelets will rise to the top. So that's an example of a suspension. Another one is that you might be familiar with is Italian dressing. Solutions are homogeneous mixtures that consist of a solvent. Most of the time, that solvent is water. It doesn't have to be, but almost always is. And then the solute is dissolved in the water in smaller amounts, or dissolved in the solvent in smaller amounts. For example, blood sugar consists of glucose, which is the solute, and then blood plasma is the solvent. Air is a gas solution. There's also salt solutions and sugar solutions. And the way that we express concentrations typically would be in percents. Like a 10% salt solution is 10 part salt to 90 part water. Whenever we are talking about blood sugar levels, blood glucose levels, like for example, typically 100 or less is what we expect for normal fasting blood glucose levels. That let's say you checked your blood glucose and with a glucose meter, and you found that it was 80. If it reads 80, what that means is 80 milligrams of glucose per deciliter of blood. And a deciliter is 1/100th of a liter. We also use molarity, but not so much in biology. As far as colloids in biology, here we go. In a cell, the fluid part, which is called the cytosol, is a colloid. similar to Jell-O. And then blood is a suspension. Moving on to section 2.4, chemical bonds, we're going to talk about, first of all, we have to talk about electrons because it is the electrons in the outermost energy level, we call those the valence electrons, for an atom that determine its chemical properties and whether or not it will combine with other atoms. So we need to understand a little bit about electrons and their location within the atom. We don't have to understand it as well as you do in chemistry class. We're not going to have to write electron configurations. And most of the elements we deal with are smaller, so they tend to follow these rules pretty well. So what we're really concerned with are the electrons in the outermost electron shell. These shells are called valence shells. The outermost shell, the one furthest from the nucleus of the atom, is called the valence shell. And these are the ones involved in chemical reactions. The octet rule determines where electrons or which shells electrons will reside in. So atoms desire 8 electrons in their valence shell, with the exception of the first electron shell, which can only hold 2. So hydrogen and helium only need 2 electrons in shell number 1, in their first electron shell, because the first shell is their valence shell and it will only hold 2 electrons. But the rest of the electron shells hold 8 electrons. Now, noble gases like helium, helium is full with 2, but for example, oh gosh, I can't think today. Noble gases like, I'm thinking of radon and krypton. Anyway, any of those noble gases have 8 valence electrons. They have 8 electrons in their outermost shell. So what's going to happen with all the rest of the atoms, which do not have 8 electrons in their valence shell? They are going to gain, lose, or share electrons with other atoms in order to fill that valence shell and complete it with 8 electrons. That's just neon is the one I was thinking of. So helium and neon are both noble gases, and both of them have complete valence shells. Helium only has 2 electrons, so its first electron shell is complete, and we consider it chemically stable, and it won't form chemical bonds. Neon has a total of 10 electrons. The first 2 go in the first shell, and then the rest, the other 8, will go in the second shell, which is the valence shell for neon. So neon has a complete valence shell of electrons. But the ones that you see here, these are 4 very common elements found in humans, in any living thing, really. Hydrogen has only 1 electron, and so it needs another electron to fill its valence shell. Carbon has 4 electrons in its valence shell, so it needs another 4. Sodium has only 1. So it either needs to gain 7 or it needs to lose that 1, because below that, in the second valence shell, that valence shell is complete if it weren't for this 1 electron in the third valence shell. So if we get rid of that 1 electron, we no longer have a third valence shell. We have the second shell is the valence shell, and it is full. So for sodium, losing an electron would make it chemically stable. For oxygen, oxygen has 6 valence shell electrons, so it would be stable if it gained 2 electrons in that valence shell. So the types of chemical bonds that we're going to learn, the most common types of chemical bonds are ionic, covalent, and hydrogen bonds. Ionic bonds form when oppositely charged ions are attracted to one another. Ions are atoms that have gained or lost electrons, and therefore they take on a charge. Because an atom, a neutral atom, has the same number of protons or positive charges as it does electrons or negative charges. So altogether it has no charge. But if it loses electrons, it's going to have a positive charge because it has more protons now. And if it gains electrons, it will have a negative charge. So an ion that has a negative charge is called an anion. That means it has gained electrons. And an ion that has a positive charge is called a cation because it has lost electrons. So an anion and a cation, which have opposite charges, are attracted to one another and form ionic bonds. The most common ionic compound is most likely, I would say, sodium chloride or table salt. It's the one that I see used in examples of ionic bonds every time I teach this chapter, and I've done it for a while now. Sodium is going to have one valence shell electron, so it needs to lose that electron to be stable. And when it does lose that electron, it's going to take on a positive charge because it will have an extra proton or positive charge. Chlorine has 7 valence shell electrons, so it will take the one that sodium lost. It will gain that electron that sodium lost. So basically, sodium will transfer that electron over to chlorine, and it will become a chloride ion, and it will have an extra electron. So that means it will have a negative charge. So now that sodium is positive and the chloride ion is negative, and they have opposite charges, they are attracted to one another, and they form an ionic bond. Most ionic compounds are salts. There are different salts besides just sodium chloride. It can be sodium bromide, magnesium chloride. There's various potassium chloride or sea salt. There's various different types of salts, but all of them are combinations of cations and anions. Then we have covalent bonds, which are formed when atoms share electrons. And they share those electrons in order to fill their valence shell. There are 2 types of covalent bonds. There are polar bonds and nonpolar bonds. So let's look at nonpolar bonds first. Okay, so we're starting with carbon, which has 4 valence shell electrons. So what does it need? It needs 4 more to have 8. And then we're starting with 4 hydrogen atoms, which each have 1 valence shell electron. And each one of these hydrogen atoms needs another electron to be stable. Okay? So what's going to happen is each of the hydrogen atoms will share 1 electron with carbon. And the carbon will share one of its 4 with each hydrogen. So if we look at each hydrogen now, each hydrogen now has 2 valence electrons, 1, 2, and the carbon has 4 extra electrons by sharing with 4 hydrogen atoms. So now the carbon has 2, 4, 6, 8 in its outer shell, giving it 8 valence electrons. So what we have is a nonpolar covalent bond. Actually, 4 nonpolar covalent bonds between carbon and 4 hydrogen atoms, and that forms a molecule of methane gas. Oxygen gas, or O2, is another nonpolar covalent molecule. So what you have is each oxygen atom has 6 valence electrons, so it will share 2 with the other oxygen atom. So what we have here is a double covalent bond, and it is nonpolar because the electrons are shared equally. And now if you count, the oxygen on the left has 1, 2, 3, 4, 5, 6, 7, 8 valence shell electrons, and the one on the right does also. And nitrogen will form 3 covalent bonds, a triple bond. So nonpolar covalent bonds are formed when the electrons that are shared between the atoms are shared equally. That's called nonpolar. Carbon dioxide is another nonpolar molecule. So it forms when the carbon forms two double bonds with one of two oxygen atoms. So this is carbon dioxide, and that is a nonpolar covalent molecule. So polar covalent bonds form when the electrons that are shared unequally. One of the atoms has a stronger pull or hold on those electrons. So if we look at water, oxygen is going to share an electron with each of two hydrogen atoms, but the oxygen atom has a stronger pull on those shared electrons, and it makes it slightly negative, have a slightly negative charge. The hydrogen atoms then would have a slightly positive charge. So you end up, it's called polar because you end up with two oppositely charged ends of the molecule. You have one end that's negative and one end that's positive. So that is what a polar covalent bond looks like. And our most common example of a polar covalent bond is water. So we have sodium chloride is our example of an ionic bond where opposite ions are attracted to one another, forms from the transfer of electrons from one atom to the other. A polar covalent bond forms when electrons are shared between atoms, but they're shared unequally. And then a nonpolar covalent bond forms when electrons are shared between atoms, but they are shared equally.